In this video, we are going to look at a generic type of reaction called electrophilic aromatic substitution, which we are going to abbreviate with the term EAS. Okay, that's the abbreviation we're going to use, and it's exemplified by this reaction right here. All right, so an electrophile, I'll just call it E+, a generic electrophile, attacks the double bond of a benzene ring, or just attacks a benzene ring, and it's going to now produce this carbocation, okay, and the hydrogen is going to go away and now produce the substituted aromatic product. The net result is that the hydrogen right here gets substituted by the E group that comes from the electrophile. All right. Okay, so if we look at this intermediate carbocation, there's something really good about it and something really bad about it. First, let's look at what's bad about it. When we made it, we destroyed aromaticity in a benzene ring. And for that reason, it's a relatively high activation energy process. And this is the reason that the benzene rings tend to be much less reactive than alkenes. Okay? All right, but once formed, there are a lot of resonance structures you can write for it. We'll just refer to this as the pentadienyl cation, which is just an allylic carbocation with an extra resonance form that we can write. Okay, so if we start writing conventional allylic resonance forms, what we see here is that we have two different resonance forms that we can write. Okay, and if we designate, or if we're looking at how this substitution occurs relative to this carbon right here, this is hypothetically the one that I've chosen that's going to be substituted. What we see here is that the carbocation position has been delocalized over the ortho and para positions relative to the carbon that gets attacked. Okay, so that's the carbon rimmer that gets attacked right there. All right, and that's going to be an important concept when we look at benzene rings that have something on them. All right, so let's look at the basic substitution reactions. First, we're going to look at halogenation. We've already seen halogenation of a double bond, and that was back in chapter 6 when we looked at halogenation of the alkene group. Okay, recall that in that reaction we add bromine, we get an anti-addition to add bromine across the carbon-carbon double bond. The carbon-carbon double bond now becomes a carbon-carbon single bond, and we add two atoms to the, or add one atom to each of the alkene carbons. Okay, but when we treat benzene with just plain old bromine, no reaction occurs. It's not till you add a catalyst that a reaction occurs. The very common catalyst is iron tribromide, shown here. And the reaction of benzene with bromine and iron tribromide produces bromobenzene and H+, and if the Lewis acid is still here, FeBr4-. We could also say that, or just think of this as being HBr. Plus FeBr3. Okay. All right, so let's look at the mechanism for this reaction. First, we're going to activate bromine with the Lewis acid catalyst, like you see here. The lone pair is, attacks the iron tribromide. This gives us now bromine, divalent here, and this is a positive charge. Okay, so remember that when we looked at bromine adding to an alkene before, we had sort of taken a bromine and polarized one bromine as partial plus and partial minus in the vicinity of the electron-rich alkene. Okay, so what we're seeing here is a situation where the more electropositive bromine, or the bromine that's being attacked, gains a greater partial positive charge character. So it's more reactive. This gives us now FeBr4 minus, which is a better leaving group than Br minus. All right, we generate this penadienyl cation shown here, and we're losing H plus to give us the product. Okay, so you may wonder, why don't we just add bromine to the carbocation to make this product? Well, it has to do with what's the energetically most favorable reaction pathway. When you look at the pathway here, going to the aromatic compound, this is energetically far better than this compound here, which no longer has an aromatic ring. So we see the chemistry that we remember from alkenes in chapter 6 being diverted to a new pathway because of the enhanced stability of benzene rings, or aromatic ring systems in general. All right, next reaction we're going to look at is nitration. And I just want to go back here and say something. Mechanistically, if we want to think about how these reactions occur, whatever our new group is, it comes in as the as a reagent that basically serves as a source of the positive charge that corresponds to that group. Okay? All right, so let's look at nitration. Nitration, we're going to take a mixture of nitric acid and sulfuric acid, and this is going to give us the nitrobenzene group, or it gives us nitrobenzene, and written out on a typewriter. It's just NO2, but this is kind of an interesting group. We need to remember the structure of it. The nitro group is a structure you cannot write without putting a formal charge somewhere. Okay, so this is the actual structure of a nitro compound. There's a resonance structure you can write involving the lone pair reacting or interacting with the other double bond, like so. Okay, so we can draw a resonance structure for any nitro compound like this that delocalizes it. Okay, let me draw a better lone pair than that. That lone pair isn't very high quality. All right. Okay, so this is a resonance interaction that's important in nitro groups. All right, so if we think about what I just said about what comes in, it must mean that somehow or another we're generating something that's equivalent to NO2 plus as our attacking electrophile. And that's in fact exactly the case here. The reaction of nitric acid and sulfuric acid is really just a dehydration reaction of nitric acid to make the nitronium cation shown here. Now the nitronium cation is a powerful electrophile. It's attacked by the benzene ring, like so, to now produce this protonated nitrobenzene, and this just loses the extra proton to produce the product. Okay, and if you notice that this mechanism and the previous mechanism are looking an awful lot alike, they're kind of repetitious, congratulations, you've really figured out electrophilic aromatic substitution. They're all going to, all of these reactions that we classify as electrophilic aromatic substitution are going to be proceeding through essentially the same mechanism. All right, sulfonation. Okay, by the analogy we just established before, it suggests that somehow or another we're generating from this combination of reagents the equivalent to SO3H+. Okay, so a benzene ring is treated with fuming sulfuric acid that's what this combination of reagents is called, will turn into the sulfonated benzene ring, and we call this type of compound sulfonic acid. All right, so sulfuric acid just simply protonates sulfuric anhydride, or SO3, to generate the SO3H cation, which is actually, in this case, the description of what's attacking it is perfectly applicable. Okay, attack at sulfur produces the cation, and we lose H+, and that produces the sulfonic acid. Okay, all right, and we'll see some special examples of sulfonic acids a little later. They're actually important antibiotics. Okay. All right. Finally, we're going to look at carbon-carbon bond formation, and this reaction here is known as the Friedel-Crafts Alkylation. Okay, so by analogy, it looks like what we're attacking has to be equivalent to R+, which of course corresponds to our old friend, the carbocation. Okay, so what we do is we take the alkyl halide and aluminum chloride, and this will add an R group to the benzene ring. There are some limitations here. The chlorine has to be attached to sp3 carbon is the first limitation we're going to encounter. What we're going to see is that our limitations are not really new. The limitations arise from carbocation chemistry and the things that carbocations do. Okay, all right, so here's an actual example where R is something. This is isopropyl chloride, and aluminum chloride produces isopropyl benzene, shown here. All right, so let's look at the mechanism for that reaction. What we're doing is we're using the chlorine group as a Lewis base. It's going to react with the Lewis acid aluminum chloride to generate this activated species here. Now, the chlorine is a better leaving group when it's complex to the Lewis acid. Okay, it leaves. This generates the carbocation, shown here. And now, as you see here, this must be the attacking electrophile that the benzene ring attacks. We generate the protonated isopropyl benzene here, this carbocation that's delocalized, and we're going to lose the H+ and regenerate our benzene ring. All right. Anything, the Friedel-Crafts, this is technically the Friedel-Crafts reaction, but we consider any attack of the carbocation on a benzene ring to be in the Friedel-Crafts family of reactions. So it's not just limited to the recipe that you see here. Any source of a carbocation can potentially initiate a Friedel-Crafts alkylation. All right? So let's look at this combination of reagents. Benzene, methyl cyclohexene, and sulfuric acid is going to produce the substituted benzene ring right here. All right, we know that alkenes are better electrophiles than benzene rings. Okay, when electrophiles attack alkenes, they generate carbocations, but they don't destroy aromatic character. So attack here is favored over attack on the benzene ring. All right, so when we look at this mechanistically, we're going to do our initial attack on the alkene to form the tertiary carbocation, and the tertiary carbocation here is analogous to the carbocation we saw in the previous slide. We generated it a different way, but it's still a carbocation. So it's going to add, it's going to generate, again, this delocalized carbocation that's not aromatic, and it's going to lose H+ to become aromatic and form the product that we see here. All right. So because this reaction involves carbocations, there's a potential complication that comes from rearrangements. All right, so here we're going to take the isobutyl cation, which is a primary chloride, And when we attempt to do the Friedel-Crafts reaction right here, what we see is that we don't really generate all that much of the expected product. Virtually none of the isobutylbenzene is formed. Instead, we form predominantly tertiary butylbenzene. Okay, and this, of course, we understand why this occurs, right? If we make this primary carbocation, it can become a tertiary carbocation simply by doing a 1,2 hydrogen shift, and this process here is going to be hard to stop. So we end up with a product that has a tertiary butyl group in it instead of an isobutyl group. Okay, so this is one complication of the Friedel-Crafts type reactions. We're going to see another complication when we look at substituted benzene rings. Okay. All right, so here's a mechanism problem. Write a mechanism for the reaction depicted, which can be described as an intramolecular Friedel-Crafts reaction. All right, so like before, we have an alkene, sulfuric acid, and a benzene ring. The first reaction that's going to occur is a reaction between the alkene group and the sulfuric acid. We're just going to protonate the alkene to now make the carbocation. Okay, sorry that I drew one of these as a methyl, one as a CH3. I just want to emphasize that we added a hydrogen at this carbon right here and made the carbocation in the process. All right, now we can have attack at this carbon right here to make a 5-membered ring. Okay, so this is now attacked. This generates, again, our delocalized carbocation. It now has a ring fused to it, but it's still basically like the carbocations that we saw before. And we're going to lose the H+. I just have the bisulfite anion coming here and taking off the proton. This proton is extremely easy to remove. You can see for obvious reasons its removal generates a neutral compound that has a benzene ring, so it's obviously not going to take very much to remove that proton right there. Okay, and this is the last of the basic reactions we're going to talk about. It's called the Friedel-Crafts Acylation. Here, we're going to take not an alkyl halide, but an acyl halide. Specifically, this functional group here is known as an acid chloride. We won't really talk about the chemistry of the acid chloride until the second half of the class, but once formed, it readily reacts with aluminum chloride and a benzene ring to produce the benzene ring that now has a C double bond O on it. Okay? All right, so for example, in this reaction, we're going to take this compound isobutyryl chloride, I guess, and aluminum chloride, and this is going to make the ketone that has a phenyl on one side of the ketone of the C double bond O group and an isopropyl group on the other side. Okay? All right, so if we think about what happens here, this group becomes that group, and it substitutes that hydrogen right there. Okay. All right, let's look at the mechanism. Mechanism is exactly like the Friedel-Crafts acylation, except that there's a important stabilizing feature to the intermediate carbocation. We're going to complex a chlorine, eliminate this group, and this is going to generate this carbocation here, which is going to be referred to as the acylium cation. And the acylium cation is stabilized by this resonance interaction right here. Okay? And so this is the actual structure of the carbocation intermediate. And because carbocation, or the positive charge, is delocalized over to oxygen, these tend not to rearrange except in rare cases, okay? But I think in this class it's never going to rearrange, okay? So because it's a stabilized carbocation, it's not going to rearrange. All right, so the carbocation here, or actually this is an acylium ion. It's not even doesn't even have a positive charge at carbon. is going to be attacked at the carbon right here, and we're going to generate again the protonated benzene ring. The extra proton is going to be readily lost to produce the product. Okay, one of the things that makes the Friedel-Crafts reaction especially useful is the fact that we can very easily get rid of this C double bond O group right here. Okay, so we're going to find that you can get rid of this group very readily, and this solves a synthetic problem here. All right, so how would we accomplish this synthetic objective here? Turn benzene into N-butylbenzene. And I'll just tell you, you can't do it in one step. You said, but what about the Friedel-Crafts alkylation? Well, you can't do that in this case because it would involve a primary carbocation that can very easily rearrange to a secondary carbocation. All right, so if you tried this reaction here, the product you would get is sec-butylbenzene. Okay, and this is because, okay, our intermediate carbocation is this one, N-butyl carbocation. We'll rearrange from primary to secondary by a simple 1,2 hydrogen shift. All right. All right, so to accomplish this process, what we would want to do is perform the Friedel-Crafts acylation reaction. Okay. Let's see if I can erase. No, I guess I can't erase something that comes from a picture like that. Sorry. But I got an extra carbon there, so let me fix that. Yeah, so that carbon, one extra carbon, sorry. So the Friedel-Crafts acylation is going to produce the Friedel-Crafts acylation product. We don't have any problems with rearrangement because it's proceeding through a stabilized carbocation. And now we can perform one of these reductions here. We're going to we're going to treat it either with a zinc mercury amalgam and HCl. This is called the Clemmensen reduction, or we're going to treat it with hydrazine and base at a high temperature, and this is called the Wolff-Kishner reduction. The Clemmensen reduction, we're not really going to talk about the mechanism for that. The Wolff-Kishner reduction, we're going to talk about that when we talk about ketones in the second half of the class, but it's a very interesting mechanism, but at its heart it's an amine reacting with a ketone, and we'll see many examples of that type of reaction in the future. All right, so this two-step alternative will successfully produce N-butylbenzene without any complications from rearrangement. All right, so this is where I'm going to end this video. In the next video, we're going to talk about, instead of using benzene as our reactant, we're going to use substituted benzenes, and we'll see that the group that's already on the benzene ring has a major impact on relative reactivity and, well, where does it go? Does it go ortho, para, or meta? Okay, so that'll be the subject of the next video.